Every year, millions of tons of plastic waste flood our oceans, suffocating marine life and threatening the entire global ecosystem. Discarded fishing nets and plastic bottles can drift for centuries, creating massive floating garbage patches that span thousands of miles. But what if this devastating environmental crisis could actually be transformed into a high-performance, highly desired everyday consumer product? Few people realize that mountains of filthy, degraded ocean plastic can be engineered into sleek, lightweight, and durable running shoes. How does an incredibly complex industrial process turn toxic ocean trash into premium athletic footwear while maintaining strict quality standards?
The journey begins far from any factory floor, out in the open waters of the world's most polluted coastal regions.
Our primary raw material is a mix of polyethylene terephthalate, commonly known as PET, alongside abandoned nylon fishing gear. These synthetic polymers were originally designed to last virtually forever, which is exactly why they are so destructive in nature. In fact, a single abandoned fishing net, known as a ghost net, can continue trapping marine life for over 500 years. Yet, this exact same extreme durability is what makes these plastics the perfect foundational ingredient for high-performance athletic wear.
The economic value of reclaiming this material is staggering, tapping into a multi-billion-dollar athletic apparel market desperately seeking sustainability. Global supply chains are now shifting, recognizing that ocean-bound plastic is no longer just garbage, it is an untapped industrial resource. However, unlike pristine factory-grade polymers, this raw material has been battered by salt water, intense ultraviolet sunlight, and abrasive ocean sand. It is covered in algae, barnacles, and chemical residues, making it one of the most difficult materials on Earth to recycle. To achieve true athletic-grade quality, this severely contaminated mess must undergo an intense, multi-stage purification and highly controlled structural reconstruction process.
The physical recovery of this plastic involves massive collaborative operations between environmental organizations, local coastal communities, and commercial vessels. Specially designed cleanup ships drag massive floating booms across the water's surface, funneling tons of floating debris into collection zones. Heavy-duty cranes then hoist these massive dripping nets of tangled plastic onto the ship decks, securing the heavily contaminated cargo. Once the vessels reach the harbor, the collected waste is compressed into giant transport bales, weighing several tons each. Convoys of industrial freight trucks transport these massive bales directly to specialized intake facilities located near major processing hubs. Upon arrival at the receiving bay, forklifts unload the compacted cubes of ocean waste onto heavy-duty industrial conveyor belts. The sheer scale of the receiving area is breathtaking, with massive concrete bunkers holding thousands of tons of raw ocean debris. Speed is crucial at this stage, as the organic matter mixed with the plastic can quickly rot and create hazardous conditions. Massive mechanical claws grab the incoming waste, dropping it into preliminary shredders that tear the tightly bound bales apart. The noise is deafening as steel blades rip through thick marine ropes, plastic bottles, and heavy industrial fishing nets. This rough initial breakdown is necessary to loosen the material, allowing the automated sorting systems to actually see what they are processing. From here, the chaotic mix of loose ocean trash is funneled onto a high-speed belt, heading straight into the decontamination zone. Before any melting can occur, the plastic must be absolutely pure. The first step in this critical phase is magnetic separation. Powerful overbelt magnets pull out any ferrous metals like stray fishing hooks or ship debris that could destroy the extrusion machinery. Next, the material enters massive rotating trommel screens, which tumble the trash to shake loose sand, rocks, and loose dirt. The conveyor then carries the waste under advanced optical sorting machines, equipped with high-speed infrared cameras and air jets. These sensors can identify the chemical signature of different plastic types in milliseconds, separating PET bottles from dense nylon nets. Precision blasts of compressed air instantly shoot non-recyclable materials off the line, ensuring only the correct polymers move forward. At this stage, even a small mistake can be disastrous. Just one rogue piece of PVC plastic can ruin an entire production batch. The sorted plastic is then fed into heavy-duty granulators, where aggressive rotary blades chop the material into thousands of small flakes. These coarse flakes immediately drop into massive industrial washing vats, filled with a highly pressurized mixture of hot water and custom detergents.
Massive agitators churn the water, creating severe friction that strips away marine algae, salt residues, and stubborn commercial adhesives. The washing process is completely closed-loop, meaning the dirty water is constantly filtered, treated, and reused to minimize environmental impact. The plastic flakes then pass through a specialized density separation tank, utilizing a simple but incredibly effective principle of physics. Heavy impurities and unwanted plastics sink to the bottom, while the valuable PET and nylon flakes float perfectly to the surface. The clean, floating flakes are skimmed off the top and sent into powerful centrifugal dryers that spin at intense speeds. Moisture is violently expelled, leaving behind millions of pristine, perfectly clean plastic flakes that look nothing like ocean trash. These purified flakes are pneumatically blown into towering storage silos, patiently waiting for the radical thermal transformation that comes next. This is where the physical transformation truly begins. The clean flakes are funneled into a massive industrial extrusion machine. Inside the extruder, a giant rotating steel screw pushes the flakes through a heavily insulated, intensely heated metal barrel. Temperatures inside the chamber reach approximately 260 degrees Celsius, precisely the melting point of the polymer. Under massive pressure and extreme heat, the solid plastic flakes rapidly break down, transitioning into a thick, glowing, viscous liquid. This molten plastic is forced through microscopic metal filters to remove any final microscopic impurities that survive the washing phase. The pure liquid polymer is then pushed through a specialized dye plate, emerging as continuous, glowing strings resembling thick spaghetti. These molten plastic strands drop immediately into a long, chilled water bath, which instantly cools and solidifies the synthetic material. The cooled strands are rapidly pulled into a high-speed pelletizer, where rotating blades chop them into tiny, uniform plastic pellets. These uniform pellets, often called resin, are the universal raw material of the modern plastic industry, ready for any application. But to make athletic shoes, these solid pellets must be transformed into soft, flexible, and incredibly strong textile yarns. The pellets are transported to a state-of-the-art spinning facility, where they are loaded into a towering melt-spinning apparatus. Once again, the pellets are melted down into a liquid state, but this time the precision required is exponentially higher. The liquid polymer is forced by high-pressure pumps through a spinneret, a heavy metal disc pierced with thousands of microscopic holes. As the liquid plastic extrudes through these tiny pores, it emerges as incredibly fine, continuous synthetic filaments, much thinner than human hair. These microscopic filaments hit a stream of precisely controlled cold air, crystallizing them instantly into solid microscopic plastic fibers. To create durable running shoe thread, dozens of these ultrafine filaments are twisted together in a high-speed drawing machine. Massive mechanical rollers stretch the twisted yarn, aligning the polymer molecules and increasing the tensile strength by over 400%. This molecular alignment is critical. Without it, the thread would easily snap under the heavy mechanical stress of running. The raw yarn is inherently white or slightly gray, meaning it must pass through giant pressurized dyeing vats for coloration. Using eco-friendly, waterless dyeing technologies, the synthetic thread is infused with vibrant, long-lasting pigments designed to resist fading and wear. The freshly dyed yarn is then wound onto massive industrial bobbins, spinning at thousands of revolutions per minute without breaking. Row after row, hundreds of heavy bobbins are stacked on automated racks, creating a vibrant wall of high-performance synthetic thread. What started as toxic, algae-covered ocean debris has successfully been engineered into a premium, incredibly strong athletic textile raw material. These massive spools of ocean-recycled yarn are now ready to be shipped to the advanced footwear manufacturing assembly floor. Inside the ultra-modern shoe assembly plant, the bobbins of recycled yarn are loaded into massive, computer-controlled knitting machines. These robotic looms are technological marvels, capable of knitting the entire upper section of a running shoe in a single seamless piece. Thousands of automated needles move in a dizzying blur, interlocking the recycled threads with microscopic precision and incredible speed. This specific manufacturing technique minimizes textile waste, using only the exact amount of yarn required to build the shoe's structural upper. By adjusting the tension of the weave, the machine creates specific zones of breathability, flexibility, and rigid structural support. Once the seamless upper is complete, automated laser cutters detach it from the main fabric roll, sealing the edges instantly with heat. The flexible textile upper must now be molded into the proper anatomical shape to comfortably support a human foot. Workers pull the knitted upper tightly over an aluminum foot-shaped mold, known in the footwear industry as a shoe last. The lasted upper passes through a specialized steam chamber where intense thermal energy shrinks the recycled synthetic fibers securely around the mold. Meanwhile, the heavy-duty soles of the running shoe are being formed in an adjacent, highly automated injection molding sector. While some soles use recycled ocean rubber, many utilize specialized EVA foam pellets that are rapidly expanded inside heavy steel molds. Massive hydraulic presses clamp the steel molds shut, applying tons of pressure as extreme heat causes the foam material to rapidly expand. The molds pop open, revealing lightweight, incredibly bouncy shoe soles, engineered to absorb massive kinetic impacts during a long run. Now, the durable ocean plastic upper and the shock-absorbing foam sole must be permanently fused together on the main assembly line. Advanced robotic arms apply a highly precise, environmentally friendly polyurethane adhesive to the exact perimeter of the foam midsole. The upper is carefully aligned with the sticky sole, and a massive pneumatic press locks the two pieces together with immense force. The freshly bonded shoe immediately travels through a specialized chilling tunnel, dropping the temperature rapidly to instantly cure and solidify the industrial glue. Any excess glue or rough textile edges are meticulously buffed away by high-speed spinning brushes, giving the footwear a flawless finish. Finally, automated lacing machines thread the shoelaces, also spun from recycled ocean plastic, through the precisely reinforced eyelets of the upper. The transformation is physically complete. An elegant, highly structured piece of athletic engineering now sits proudly on the factory conveyor belt. Before any shoe can leave the factory, it must survive a brutal, uncompromising series of physical and structural quality control tests. High-resolution optical scanners inspect the upper fabric for any dropped stitches, uneven dye distribution, or tiny structural imperfections in the weave. If the cameras detect even a millimeter of misalignment in the logo or the stitching, the shoe is instantly flagged for rejection. Next, random samples are placed onto a relentless mechanical flexing machine that simulates the exact biomechanics of a human running. Heavy metal pistons repeatedly bend the shoe thousands of times per minute to ensure the ocean plastic threads will not snap under stress. A powerful pneumatic claw grips the sole and the upper, pulling them in opposite directions to test the sheer strength of the adhesive bond. Specialized abrasion wheels grind aggressively against the outer sole to guarantee the material can withstand hundreds of miles of harsh asphalt. Trained human inspectors perform the final tactile review, running their hands inside the shoe to check for any irritating internal seams. Shoes that fail these rigorous standards are not thrown away. Instead, they are ground down and completely re-entered into the recycling loop. Only the flawless pairs, perfectly balancing lightweight agility with extreme durability, are granted the final stamp of manufacturing approval. The approved sneakers enter the final automated packaging sector, where they are gently stuffed with recycled paper to hold their optimal shape. Swift robotic arms pick up the pairs and place them into custom-designed shoeboxes entirely constructed from unbleached post-consumer recycled cardboard. Automated labeling machines instantly print and apply a unique barcode detailing the shoe's exact size, colorway, and specific manufacturing batch number. The individual boxes are rapidly grouped together and sealed inside massive, heavy-duty master shipping cartons for long-distance international transport. Huge industrial palletizers stack the cartons into towering, perfectly balanced geometric cubes, wrapping them tightly in secure transit film. Heavy forklifts navigate the cavernous, brightly lit warehouse, loading the heavy pallets directly into the steel bellies of waiting shipping containers. From this massive logistics hub, the eco-friendly footwear is distributed to premium retail stores, sports boutiques, and eager customers worldwide. The shoes are transported across the very same oceans that they were painstakingly rescued from, but this time as a high-value cargo. What was once considered an impossible environmental burden has now successfully been integrated into the massive global retail supply chain. The transformation of destructive ocean waste into elite athletic wear is a profound testament to modern industrial engineering and human ingenuity. Every pair of these shoes removes around 11 plastic bottles from the environment, proving that sustainability can actually drive mass production. By reimagining our global supply chains, we can physically extract our past environmental mistakes and weave them into a better future. This complex journey reveals that trash is just a failure of imagination, and raw material is simply waiting to be rediscovered. The next time you lace up your running shoes, remember the extraordinary, deeply transformative journey those synthetic threads have survived. Because true innovation does not just create something entirely new, it finds incredible, lasting value in the things we have left behind.